Right, well, now we're gonna actually start doing calculus with these things that we've been talking about so far. So section 14.2 is about finding derivatives and doing integrals with vector valued functions. We'll start with derivatives, and for that I want you to recall how the derivative of a ordinary function looked. You probably saw it as either f prime at t or df dt. This is notation that comes to us via, basically it's what Newton would have used. He had a dot rather than a prime, but it's sort of reminiscent of Newton's notation, and this is called the Leibniz notation. I think folks prefer this, but you're soon going to see that the Leibniz notation is really handier when we get into vector manipulations later, especially things like the Green's theorem and integrating vector fields and things like that. Well, let's say it in terms of the Newton notation style. The derivative of f prime at t. Oh, previously you probably saw this with x in there, but that's just changing the letter. I'm going to change another letter on you too. Is you did it as the limit. It was always h. H goes to 0 of what did it look like? F of x plus h minus f of x. Darn it. I was trying to change the letter to t, and then, my brain made it be x again. Sorry. Those are supposed to be t's now. It's actually not that big of a difference, but, you can't mix and match like that. And then we'll be dividing by h. So as h gets smaller and smaller, this piece gets smaller and smaller, but then we're dividing by something that's getting small, so that scales it back up. You end up getting the derivative, the slope of the function, the slope of a tangent line to the function, to be more precise. Well, we're going to do this same thing with r, but let me just write this on the side. Remember that we normally have to specify component functions for r, and they, at least in the book, they go with f of t, g of t, and h of t. And that is a little bit sad for our use. The z coordinate function is h, but we were using h for the limit variable. So no big deal, we'll just change letters. The limiting value variable won't be h anymore. I'm going to make it be, what do you think? Maybe s. I like s. So take all the h's and turn them into s's. No big deal. That's still the limit. The limiting the variable you use in the limit actually goes away when you do the limiting process. So we end up with something that's strictly a function of t. And now that we're using s as the thing that's going to 0, we can say this in terms of our vector function. So I wrote it up here. Let me try to make sure this doesn't get lost. That's just let's say a standard way to refer to the position vector r of t. I'd like to get the derivative of r of t. And we just work by analogy. It should be the limit with s going to 0 of r evaluated at t plus s minus r evaluated just at t, all divided by s. So in other words, it looks just like the thing above. In fact, it's sort of bleeding into the thing above. I'm putting a line and go across the board so you can tell them apart. Well, now if I finally re-express this in terms of the f, g, and h component functions, I don't know if I've got room for it, but no, there's no sense in me being this stingy with board space. Let me just do a quick erase, and we'll continue at the top of the screen, top of the board. I'm going to leave what's below the line there, though, so that we can refer to it. All right, so that's equal to, one thing I noticed while I was about to write that is that I was going to need more space, so there's a little bit of room pulled back this way. Let me do that. Okay, we'll have the limit as s goes to 0. We'll have this big fraction with s in the bottom of it. But upstairs, we're going to need the vector r, vector function r, evaluated at t plus s. That looks like this. It's got f at t plus s, and g at t plus s, and h at t plus s. And that was the end of the first vector. That's r at t plus s. We need to subtract r at t. Is there going to be space for this? I hope. It's the vector with f of t, whoops, g of t, and h of t in it. I do seem to be out of room for the vector brace at the end of that mess, but there you go. Well, in fact, you can also combine these vectors into a single thing, into a single vector. And it looks like it's got an s in the bottom of this fraction. In the top, in the x coordinate, we'll have f at t plus s minus f at t. In the y coordinate, we'll have same thing but with g's in it. G of t plus s minus g of t. And in the z coordinate, it's h of t plus s and h of t. Now, I don't know if I can justify this. Yeah, I can. Remember how we said what you did with the limit when you were applying the limit to something that was a vector? You just distribute it. You just bring it to the inside. And this, taking a big vector here and dividing it by s, I could turn that into divide each of its components by s. So let me do two things at once here. What we've got is a giant vector which has in the x coordinate the limit as s goes to 0 of f of t plus s minus f of t over s. That's the x coordinate of the thing. What's the y coordinate of this big old vector? Again, it's got this limit, and it's g of t plus s minus g of t over s. And the z component, well, I may not have space for the z component, but you know what it's going to look like. It'll be the limit as s goes to 0 of, well, it's the difference quotient with h of t, maybe if I write really tiny. And then angle brace for the back end of that vector. Well, you know what? Do you recognize those things that are now the components of this thing we've created? I hope you do. That's the derivative of f. This one's the derivative of g. And that last scrunched in one is the derivative of h. So what we've produced here is a vector that's got f prime at t, g prime at t, and h prime at t as its components. Which is a really long-winded and maybe slightly irritating way to arrive at it. But what it says to us is, you got a vector, you want to take its derivative? Just take the derivative of its components. It's that easy. So let's put it in use. Let me do an example of that. Actually, let's just start fresh and do an example. one of the space curves that I showed you in the previous video was this one. The things I did on CoCalc. It had t squared and t cubed as its component functions. You want to take its derivative? Totally easy. Just take the derivative of t. We are talking about the derivative with respect to t. So derivative of t with respect to t is 1. And t squared becomes 2t. And t cubed becomes 3t squared. Right? Totally easy to do. Do you remember the helix? The R function for that, well, there's many variants we could do depending on sort of the slope of the spiral, but let's do cos t, sine t, and t, just for simplicity's sake. What's the derivative? Derivative of cosine is minus sine. Derivative of sine is cosine. And derivative of t is 1. So, except for the way the parameterization is laid out, this is the helix. Do you recognize what this would be? The mixture of sine and cosine tells us that we're drawing a circle and we're at a height of z equals 1. The derivative of the helix is the circle that's floating in midair, 1 unit up along the z-axis. It's not the usual circle, which would go cosine sine, but it is still a circle. It's actually just 90 degrees around. We start tracing when t equals 0, where the circle is crossing the y-axis. Not to worry, it's still a circle. All right, what is the meaning of this? Well, let me try to draw for you the helix, and at the same time, or maybe in parallel to it, the circle floating up in the air. When you're at a point on the helix, which normally corresponds to t equals 0, you're 1 unit out. If this is the unit circle, or actually this helix, it is the unit circle. At t equals 0, your axes would look like that. So you're at the point, or we could do it as a vector too, but let's say it's a point 1, 0, 0. Now, what is the point on the floating circle that corresponds to t equals 0? Sine of 0 is 0. Cosine of 0 is 1. We're looking for the point, or the vector, 0, 1, 1. That's 0 in the x direction, 1 in the y direction, and 1, well, the whole circle is up. So it's there. It's parallel to the y-axis, right? It's one unit out in the y direction, and it's 1 unit up in the z direction, and it's 0 in the x direction. So what's that guy? Let me try to interpret that guy as a vector. It looks like that, right? It goes from the origin there. That's a position vector. And that is exactly which way this curve is going, right there. It's the direction of motion of that curve. It doesn't look that close to it, given the way I sketched it, because my sketch is actually a little bit off. It should have been more like that. Going through there, so the slope would look right. But, well, the important thing is to think about what this derivative does for you. The derivative in an ordinary function gives you a slope, which is sort of the best way to think of the slope is, how is the function changing? Well, if you're on a vector space curve, how the function is changing is a change in position. Let's make a little picture, not of any particular graph, but of just sort of a generic space curve, and think about what's what's the geometric interpretation of our definition of differentiation? So, you know, big picture. Here's a coordinate system down in the corner here. We're going to be talking about a position vector, r of t. If suppose that's the positive orientation, so this tip of this thing is on the curve at time equal t, at time equal t plus h, we're down here. I'm going to have it break over the label there. So this would be r at t plus h. Now what's, remember how we were doing this, the limit, can't use h, s going to 0 of r of t plus s minus r of t all over s. I was bad before I got stuck in using h, but remember we had a name collision that can't be h anymore, so s. R at t here, r at t. How about if I just change where that label is, because it's annoying to break the vector. There's the vector. This first vector is our r evaluated at t. The other one is that. What vector do you get when you subtract? The later one minus the earlier one. I was hoping to go for red, but here's a green marker. It's there. And what happens is I take the limit, let s get smaller, this guy gets smaller. But then we divide by that length, which makes it bigger again, because s is, you should think of s as being a relatively little number, right? It's going towards 0. When you divide by something small, that's like multiplying by something big. So the vector shrinks, and then we divide by s, which makes it grow again. In other words, this limit actually exists, and the vector that it's converging on has a nice, good size, palpable size there. That's the interpretation of r prime at t. Now, is it fairly evident that that vector that was the difference in there is pointing mostly along the direction of the curve? Not at first. You know, when the distance between, I should say the time difference between r of t and r of t plus s is fairly big. Like if s is 3, we're way down here, and then the vector is not pointing along the curve. But as we come in, as we let s get smaller and smaller, we get a vector that is pointing really exactly in the direction of motion along the curve as when the limiting value goes towards 0. So that's a tangent vector. There is a pretty useful idea that comes in, which is to say, well, think about it this way. You could be following the same curve multiple ways. I just traced it about 3 seconds from end to end. But I could go, right? Or I could just take my time tracing along this curve. These are just different parameterizations. They would have vastly different tangent vectors. The super fast one has a great long tangent vector. The really measly slow one has a very tiny tangent vector. If you try to do the geometry of the curve as opposed to the parameterization of the curve, you just want to know what's the direction of the tangent line. And so to get that, you would like what's known as a unit tangent vector. By long tradition, the unit tangent vector is called t, capital T, and it's a function of t, little t. So t for tangent as a function of time, t for time. We use capital and lowercase to make sure we distinguish the two different t's. Well, to get a unit tangent vector, that is a vector of length 1, all you need to do is take this vector, the derivative, and scale it appropriately. And it turns out the appropriate thing to do is just divide it by its own length. because then you'll get something that's got length 1. So divide r prime of t by r prime of t's size, absolute value, or length of it as a vector. Let's do a quick example of that, and then we'll move on to some other fun stuff. One of the spirals, one of the curves that I showed you in the co-calc session before was the thing that spiraled outward in the xy plane. So its coordinates were, well, the one I showed you wasn't this, but this is close enough. T times cos t, t times sine t, and 0. That's a spiral, not a helix. It stays in the plane z equals 0, and you can think of it as tracing around a circle whose radius is getting bigger and bigger and bigger as we go. Yeah. So what's its derivative? Oh goodness, well, do you remember the product rule and quotient rule and things like that? You better, because we're going to be seeing them again real soon. This is a product of two things, so I'll need the first times the derivative of the second, plus the derivative of the first times the second unchanged. That was the x coordinate. The y coordinate is going to be the first times the derivative of the second, plus the derivative of the first times the second unchanged. And of course the z coordinate was already 0, so when we take the derivative of any constant, we get 0. I feel like we should do a little simplifying on that. That is cos t minus t sine t. This is sine t plus t cos t. And 0 is the last thing. So we've got our derivative. Can we figure out how long that thing is? Yikes. I'm wishing I'd picked an easier example, but oh well. We want to know the length of r prime of t. Square root of the sum of the squares. Yeah. So we're going to square that. And square that. Squaring 0 I can handle, but squaring this one, well, it's a FOIL rule deal. So first times first is cos t times minus t sine t. What am I talking about? First times first is cos t times cos t. That's cos squared t. Outer times outer is that other thing I just described. Cos t times minus t sine t. And inner times inner is that same thing. So the O and the I from the FOIL rule give us 2t cos t sine t. And then last times last gives us the minus sign is going to cancel because there's two negative terms in that. So we end up with t squared sine squared t. Positive. Okay, that was all just from the first guy. We've got to do the same process of FOIL rolling out the second guy to get its square. So we're still under the same radical. I hope that looks weird, but I think it'll be all right. Anyway, we got sine squared t. Outer times outer will be t sine t cos t. Inner times inner will be t sine t cos t. We're going to get plus 2 guess I can say this cos t sine t. And then last times last is going to be t squared cos squared t. All right, cool, because some stuff cancels. This term that had a minus sign and this term that had a plus sign are identical except for that sign, so they're gone. You can put the cos squared and the sine squared together. And then you can also put together the t squared sine squared t and the t squared cos squared t. I think I just did the order wrong in that, but oh well, that's fine. And there's a lot of nice stuff here. Cos squared t, sine squared t, those guys add up to 1. And these guys would add up to t squared. So what we've got now is the square root. It actually simplifies quite a lot. Square root of 1 plus t squared. That's an expression for the length of our tangent vector. The whole point of getting that was so that we could take we could find the unit tangent vector. I'm going to save there because we need that expression for r prime of t. But up here, let's figure out what t of t is. The unit tangent vector. Well, it's just going to be divide by square root of 1 plus t squared. So I'll write it as 1 over square root of 1 plus t squared up front. And then we'll have the rest of the terms of this. I need to make a nicer angle brace. All right, cos t, well, I'm just copying, aren't I? Cos t minus t sine t. Sine t plus cos t, sine t plus t cos t, and 0. You know, again, a space curve, something that we could definitely plot in Sage or CoCalc and see what it looks like. Okay, the next place we need to go is page 878 in the textbook. And on page 878, there is a table with a box around it, and it's called Theorem 14.1. So we're going to need to run through it. It is actually pretty quick to run through, even though it's a big, scary-looking table, because everything in it is analogous to stuff we've done before. It's just things being turned into vectors that were previously not vectors. Page 878. Theorem 14.1. Really? 14.1. Okay. This is the very first theorem we've run into in chapter 14. That's why it's labeled like that. The first thing in the box is the derivative of a constant vector. Now this is written like this, d by dt of c. And if I just wrote it the way it was in the book on the board, you would be like, no, I don't even understand. This is no different from anything before. The difference is in typography here. In the book, this C is boldface, and this 0 is boldface. I'm not going to keep trying to write bold-faced things on a chalk or on a whiteboard, so let's adopt the use vector hats standard here. So we'll say the time derivative of a vector c is equal to the 0 vector. Because if you have just a fixed vector that's got just raw numbers in it, no time dependence, then its derivative is the 0 vector. And that's the same thing it was previously except vectors on the parts. This is called the constant rule. This is like when you took the derivative of 2 and you got 0. So that's part 1. Totally the same thing as what we were doing before. The derivative, this is number 2, of a sum. That's what are we using in the book? U and V. Vector U of t plus vector V of t. I better parenthesize this so we see the order properly. So we're differentiating the sum of these two vectors. Well, how did that work when you had functions? If it was d by dx of f plus g, when you're just at, well, you just distribute the derivative. So that's what happens with vectors. You get d by dt of u, which depends on t, plus d by dt of v, a function of t. And that, very imaginatively, was named the sum rule. Now, let's see, do you remember other rules that you used in Calc 1? Well, you should have learned it in Calc 1. You had the product rule, you had the chain rule. What else? The quotient rule. The quotient rule really is not going to make sense in our setting. Do we know how to take a vector and divide it by a vector? We can take a vector and divide by the length of a vector, but no, we can't just divide a vector by a vector. So there is not going to be a quotient rule. You'll notice there is no quotient rule in this 14.1 table thing. What there are 3 different product rules, because we have 3 different ways to multiply things involving vectors. So the way they did it in the book is they did the first product rule, then they did the chain rule, and then they came back for the other 2 product rules. I think I want to run the product rules all together because they're all the same. So let's look at the chain rule. The chain rule is, well, the chain rule is about, so this is actually number 4 as it's labeled in the book. A chain is actually a way they refer to the composition of functions. So maybe I should just remind you how this looked when we were in regular functions. It was for taking the derivative of f of g of x. And the derivative of that was, you took the derivative of the outer function, you just stuck g of x into it like it was in its, you know, the original f had g of x in it, so f prime has g of x in it. But that's not quite the whole story. You have to also multiply by g prime. Remember doing that? You must have. You did plenty of those when you were in Calc 2. So that's what we're going to see for vectors. The difference is one of these, you know, there's an asymmetry here going on. One of these things can be a vector and the other a scalar, but not vice versa. So would it make sense to have a scalar function like f applied to a vector input of t? Could you make sense of that? I don't think so. If f is supposed to be a scalar function, it needs a single number as an input, and this is 3 or maybe more numbers. So that doesn't make sense. But if we had a vector and instead of just t in it, it had some f of t, that does make sense. That's sort of changing the time parameter before you feed it into the vector, which, you know, you can do that. You've still got something that can be computed, whereas this just didn't make any sense. Excuse me. So the chain rule is going to look like so. I was just putting that stuff up there to sort of feed you into thinking about the chain rule. Let me erase it and write the correct chain rule down. We're taking the derivative with respect to time of something that looks like I believe in the book it's u, so let's use u. You applied, or you evaluated it f of t. That's what we want the derivative of. And it looks entirely analogous to what you did for what I just wrote down for the chain rule. You take the derivative of the outer thing, which is u prime. You evaluate that at the inner thing. And then you scale things by the derivative of the inner thing. That's the chain rule. And that's something you can prove. I think that, yeah, immediately following the theorem, there's a proof of the chain rule. I would like you to see if you can follow through that argument, because it's not that hard, and it's good brain exercise, really, to try to follow the through on the proof. Okay, so great. Let's do 3, which I just skipped over, and then 5 and 6. Those are the various product rules. So 3 is the scalar product rule. By which I mean we're having a function of time, just a scalar function times a vector, also a function of time. And that's what we want to take the time derivative of. How the product rule worked in the past? You took the first times the derivative of the second, and then you added on the derivative of the first times the second with no change made to it. And that's what you do here. So I mean, it's literally, the only difference is that we put some vector hats on the u's. Other than that, it's really just the same exact thing as the product rule. But we've got, this is multiplying a scalar times a vector. We've got other ways to do the products. And it turns out they all obey the same product rule. It's cool. So we can have the dot product rule. And that looks like this. You're taking the time derivative, oops, put the t in the wrong place. You're taking the time derivative of a dot product of u of t dotted with v of t. But don't sweat it. You just do the first times the derivative of the second plus the derivative of the first times the second. Now, it's interesting, and I want to point this out to you. There are several dots in the last two things. You have to ask yourself what they mean. What does that dot mean? What does that dot mean? Those are lying in between a scalar and a vector. So that is multiplying a scalar by, multiplying a vector by a scalar. That, in other words, those guys are the scalar vector product. There's dots on this next line here, and there, if you like. What are all of those? Those guys are dot products. You have to be able to distinguish them, and you can by context. This dot is in between two vectors. Does it look like a constant times a vector? No, it's vector times a vector, so it's a dot product. So are these other ones. These other dots lie between two vectors. They have to be dot products. The last product rule is when we're trying to take the derivative of a cross product. I numbered this one wrong, it's 5, isn't it? And the last one, 6, is the time derivative of a cross product, u of t crossed with v of t. I just noticed that the book's version of this is going to come out in the other order than my version, but I mean the other order in the sum, so it's not material, it doesn't change anything. All right, so I always do it as the derivative of the first thing unchanged times the derivative of the second. I think that's probably wrong. Right, so, and that x is correct, right? This was the cross product rule, and so the multiplications in it are going to be cross products. Yeah. Well, so if you look at it in the right light, we got nothing new to learn here. It's just do the regular old product rule like we had before, and keep the things, the multiplication things with whatever you were doing. If you were taking the derivative of a dot product, then you're going to have dot products in the product rule. If you were taking the derivative of a cross product, then you'll have cross products in the product rule. And if it was scalar products, scalar products. So, not really that big a deal. Very useful though for certain computations. Like, for instance, this one is really neat when you see it in like figuring out Kepler's laws of orbital motion, and we get to do stuff like that in this course, which is fun. Next topic is higher order derivatives. Can we take more than one derivative? So let me return to one of the first examples we had. R of t was t squared, t cubed. And then r prime was 1, 2t, 3t squared. By high order derivatives, I mean keep going like this. Now take a derivative of the derivative. We'll have r double prime of t. That would be 0, 2, and 6t. I could have r triple prime of t, which would be 0, 0, and 6. After about 3 primes, people usually switch it up and just put a number in parentheses up there. So we could have r's fourth derivative, but that's actually not very interesting here because what is it going to be? We've got a constant vector for the third derivative, so we're going to get a 0 vector for the fourth. Higher order derivatives. You get these in vector valued functions. For instance, if r here is a position vector, then r prime is a velocity vector. Do you know what r double prime is? That is called an acceleration vector. R triple prime is known as jerk. And there is a name for R4, but I can't remember it, the fourth derivative of motion. If it comes back to me, I'll let you know, or you can Google it. Name, what is the fourth derivative of motion called? Fourth derivative of position called. Okay, so that's enough of talking about derivatives. The other calculus operation is integration. How does it look if we try to integrate a vector? Well, you probably recall there's 2 different styles of integrating. Definite and indefinite integrals. Definite integrals are the kinds where you have limits, upper and lower limits. Indefinite integrals are the kind where you had to do a plus c on the end because you didn't have limits, and so there's an arbitrary constant that turns up in the process of integrating. Let's do an indefinite integral. Let's do an indefinite integral first. We learned a little bit of a lesson with derivatives, didn't we? That you just take the derivative of the components. Integrals are going to work out the same way. You just take the integral of the components. And if it's indefinite, you're going to get a plus c on each one of those integrals. Let's look at an example. Suppose we wanted to take the indefinite integral of the function, the vector valued function. Well, let's use that one I've been using, t squared, t cubed, with respect to time. No limits on this integral, so we don't have that part. It's okay, you just take, well, I guess I should write it out. What you do is you create a vector that has the integral of the components. And that's easy enough to do. What do you get then? You get, in the first component, you get p squared over 2 plus a constant. That's in the first component, and I'm going to get constants in the other ones too, so let's call this one c1. Next, we're going to get t cubed over 3 is the integral. And it has its constant, c2. And finally, t to the 4th over 4. Oh, it's not a plus, sorry, it's a comma. Now, you could view this as split up into two things. A vector that has these powers of t, you know, the sort of actual functional part, and then another vector that has the constants in it. That's actually probably a good way to think of it, in fact. Think of this as the sum of two vectors. One just looks like the raw integrals, the antiderivative of the vector we had there. And then a constant, so it's a constant vector. So it's got those three components in it, C1, C2, and C3. All right, so that was an indefinite integral. How about a definite integral? Let's do something a little more fun. How about one of our helices? About the integral of cos t, sine t, t. And we will take that from 0 to pi. Definite integral needs to have limits, so a lower limit and an upper limit. Well, you just did, whoops, left off my tail of the thing. You're always supposed to say d something at the end. In this case, it's dt. So I could do like this, where I get the functional part plus constants, but when we evaluate at the upper limit, we'll have those constants, and then we evaluate at the lower limit, we'll still have those constants, and when we subtract, they're going to go away. So you don't need to carry any constants along when you're doing a definite integral. The fundamental theorem of calculus means you subtract your evaluation at the two endpoints. So, yeah. So this is just integrate cosine. Oh. Nice memory trick. I find people really enjoy this because for some reason cosine and sine, and when we're integrating and differentiating, it's hard to keep straight. But if you make this little diagram, which has the order in which you run through those four functions, the cosine and the sine both plus and minus. If you, the arrows I've just drawn are for differentiating. So that's d by dt. Right? And if you need to go backwards, you'll be integrating or anti-differentiating. So I want the antiderivative of cosine, it's sine. The antiderivative of sine is minus cosine. I don't need that wheel to do the antiderivative of t. It's t squared over 2. But we need to evaluate between 0 and pi. So at the upper limit, sine of pi is 0. The negative of the cosine of pi, I think that's plus 1. And then pi squared over 2. And then let's subtract what we get at the lower limit. Sine of 0 is, oh, that's 0 too. Negative cosine of 0, cosine is 1 at 0, so negative, that's minus 1. And 0 squared over 2 is 0. And finally, we can actually put these two together, right? We can subtract. 0 minus 0, okay, that's not interesting. 1 minus minus 1, we got a 2. Pi squared over 2 minus 0, okay. That's a definite integral. Now, it's sort of interesting that the answer, what is the meaning of doing an integral? And the answer came out to be another vector. That's intriguing. Well, we're going to see what these things, what the meaning of them in the next section, so don't get worried about it, but it's cool what the meaning of it is. When you take the derivative of position, you get velocity. Suppose you know what velocity is, integrate, and you'll get position. Of course, you may be a little bit uncertain about where you start, and that's what the constants do. But if you have limits like this, what you get is the change in the position over that range of intervals, or over that interval. All right, babbling now, stopping this. That's it for today. We've actually covered 2 sections in one day. Hopefully, well, we have 2 hours on Monday, so that's horrible, but I was still planning to do another CoCalc/Sage worksheet with you guys on Monday. So I don't think we'll have cut too much into the time for learning to do computer algebra. In any case, thanks. I hope you enjoy the rest of your weekend. These are getting posted Saturday night, so you should have plenty of time on Sunday or Monday morning to have a look.